All right, so last time we left off talking about NP-completeness, particularly the Cook-Levine theorem. We talked about transformations, reductions from one problem to another. We showed Cook's paper, reducing all of NP to satisfiability, which makes it the hardest problem in NP in that sense. Everything reduces to it in polynomial time. Leonid Levine also did the same thing. It didn't get as much credit for historical reasons. And we said NP-completeness, among many other things, allows you to say things like, I couldn't solve this problem, but it wasn't for lack of trying, it wasn't for lack of intelligence, it's because it's NP-complete. And so if I solve this problem at hand, I'm also solving everything in NP as well in polynomial time. So it's a very powerful theory allowing you to explain why you can't accomplish certain things efficiently, right? Because in some sense you're accomplishing a large class of things then efficiently, all of which resisted efficient solutions for many decades by thousands of smart people. So that's a tall order to expect you to do that. All right, we mentioned that the class P and NP are robust, they're model independent, they apply to all these models. We mentioned that there's different reduction types. We're not going to go too much into that, but you can have a reductionist in one fell swoop transformation or repeated calls to a subroutine or oracle, or however you want to think about it. It's still an open question whether the two are equivalent, whether class NP is invariant under these two different types of reductions. And towards the end, we mentioned Boolean 3-SAT, which is a restricted version of SAT where every clause has 3 variables or negated variables only. Turns out it's not any easier than regular SAT because you can transform large clauses into a few small clauses, a linear number of small clauses. It's, again, a polynomial time reduction, which proves that 3-SAT is NP-complete as well. We mentioned that 1-SAT is trivial, and 2-SAT we kind of left open. We said it's polynomially solvable, but didn't say how. Maybe for extra credit, show how. Then we went through a catalog of different problems, finding cliques in graphs, complete graphs of size k, set cover, trying to cover a set with the minimum number of subsets. We said all of these are NP-complete. Hamiltonian cycles, a cycle through a graph touching every node once. If you want to touch every edge once, that's a lot easier. That's an Euler tour. There's a linear time algorithm for that. But every edge once, touching every node exactly once, that's a different story. That's much harder. Graph coloring, whether a graph is colorable and using 3 colors where no 2 adjacent neighbors share the same color. Again, NP-complete. Lots and lots of books on each of these problems. They're very, very classical, important, ubiquitous. Partition, given a set of integers, partition into 2 subsets, both of which have the same sum. Innocent-looking problems. A knapsack problem, right? You have a maximum weight limit, and you want to maximize the value of the items you put in that bag out of the collection of items you have at hand. What you want to do in a burning house, say, or when you go camping for that matter. Bin packing, putting a lot of objects into a restricted space, wasting the least amount of empty space. You can do it in 1 dimension, in 2 dimensions, in 3 dimensions. When you move your household, you try to solve this problem. FedEx tries to solve this problem every time you deliver packages every single day. Steiner tree, I think that's where we left off. You have a bunch of points, you want to connect them, or you want to minimize the total interconnect length. If you're not allowed to use extra points, that's minimum spanning trees. Those are easy. You got Kruskal's algorithm, you got Prim's algorithm. How many have a Prim or Kruskal minimum spanning trees? Okay, good. So you've had algorithms. Easy to do, but if you're allowed to add extra points, not so easy. Here we're adding an extra point in the middle other than the 3 we're trying to connect in blue. And the question is, if you have a lot of points in blue, where do you put all the red points that are extra points that you're inventing to reduce the overall interconnect length? Very, very tough problem. And it's, again, ubiquitous. Every time you build a building, you're solving this problem. Every time you're connecting houses with fiber optic in a neighborhood, you're solving this problem. Every time you run electric grids across your city or state, you're solving this problem, and so on and so on. Interconnects are very, very ubiquitous. And you can do it in graphs where you have a graph, you want to interconnect the blues. The reds are there, but you don't have to interconnect them, but you can use them as intermediary points to reduce their overall length like you did here, except that's the graph version. It's not a geometric version. Again, a solution might be this spanning tree in red, spanning all the blues and a few of the reds because it makes it cheaper, but not necessarily all the reds. So I actually worked on that problem among others in this class, NP, and I have the world's best performing algorithm for general weighted graphs, actually. It's been held that record for over a decade. Lots of books on this problem, very ubiquitous. Again, it's NP-complete, and it's one of Karp's original set of problems that he proved NP-complete on the heels of Cook's theorem back in the early 70s. We're about to see Karp's paper in more detail. Traveling salesperson, very similar to Hamiltonian cycle. You want to not just connect a bunch of things, but minimize your overall length, which is what you want to do when you travel, and you want to hit some destinations, minimizing distance traveled, time traveled, airfare cost, whatever your metric is. Again, many books on this. I came up with a variant once that the points can actually move around. They're not stationary. So it's moving target, TSP, traveling salesperson. It's no longer fixed points. And you might imagine applications of this like ships at sea. You want to service them or reach them, or targets that move around in a hostile scenario. You want to service them, which means you're bombing them basically. And they're moving around like Scud missile launchers or whatever in the desert. That's even harder because if they're stationary, it's hard enough. It's already NP-complete. If they're moving around, well, stationary is a special case of that. So you can imagine how difficult that is. We have some interesting heuristics for it, though. And we'll see some heuristics. This is a traveling salesman map of all the towns and cities of the U.S. So a presidential candidate wants to visit every single town. We'll have to take a tour. It looks like this. Some edges are over water, actually. So graph colorability, let's look at it more specifically. You have a graph. The question is, do k colors suffice? K could be 3 or some larger number to color the graph such that no two adjacent nodes share the same color. So for example, for this graph, here's a coloring. No two adjacent nodes share the same color. For this graph, there's a coloring. And in general, it seems innocent enough, at least for examples like that are small. But in general, nobody has an efficient algorithm for it, and it's NP-complete. And you can look at all possibilities. That's a brute force algorithm. Try all possible ways of painting the graph. There's an exponential number of them. But that's not an efficient algorithm because there's an exponential number of them. That's no big feat to do that. So anyway, here's Karp's paper. It was 1972. And basically, he says, we showed that a large number of classic unsolved problems of covering, matching, packing, routing, assignment, sequencing, blah, 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 are equivalent in the sense that either each of them possesses a polynomial bounded algorithm or none of them does. So he's bundling all these problems together. That's the contribution of this paper. He's showing that they're NP-complete. Of course, at that time, the term NP-complete, quote unquote, was just being invented. So here it's just calling them equivalent, but really it's NP-complete. And he gives, of course, Cook credit here. He says this paper was stimulated by the work of Stephen Cook, 1971. The rest an important theorem which appears in his paper. We've already seen Cook's theorem, reducing all of NP to satisfiability via reduction of a generic Turing machine computation. It's non-deterministic. Coming up with a large Boolean formula is satisfiable if and only if that Turing machine halts on its input. So he defines a class P and talks about deterministic algorithms or Turing machines. He talks about problems are solvable in polynomial time. He talks about string recognition, reducibilities. There's that ubiquitous notion of reducibility, the two ovals A to B with this function that reduces members of A to members of B and non-members of A to non-members of B. So he explains all that. And then he lists a lot of problems. Here's satisfiability with 2 literals per clause. And we already said that's efficiently solvable. We didn't say how, but for extra credit, tell me how. 3 satisfiability, we already mentioned it's NP-complete. And he talks about, again, Cook's theorem and non-deterministic algorithms. And he then goes on to say satisfiability is in NP and it's NP-complete. That's Cook's theorem. But then he says the same is true for all these other problems here, and he gives a long list. And the list includes clique, which we mentioned, set backing, set covering, right, Hamiltonian cycle, all the ones that we mentioned and a bunch more too, because we didn't go through all 20 some of them. And basically, he calls them complete problems, and now we're calling them NP-complete problems. But this paper, and this section of this paper, basically invents the theory of NP-completeness on top of Cook's theorem, which kind of ushered it in with one problem. He's saying, well, there's lots and lots of other problems that have the same property, that all of NP reduces to that in polynomial time. There's nothing special about satisfiability that has this property. And then he goes on and listing a bunch more. Right? Chromatic number, that's graph coloring. Steiner tree, which you mentioned, interconnecting points with the least amount of total length. Knapsack, right, trying to backpack and maximize your value, given that you only can carry so many pounds, and so on, a bunch of others. And then he starts giving reductions, transformations of one to the other, and showing that they're all NP-complete. So satisfiability, we already know is NP-complete by Cook's theorem. So we know that all of NP reduces to satisfiability up here. And then he shows how satisfiability can be reduced to clique, and how satisfiability can be reduced to 3 satisfiability. Satisfiability with most 3 literals per clause, now we call it 3-sat. This reduction we already did. How many remember that? Right. Yes. Long clauses become short clauses, right? So this reduction we already did. And then he shows how to reduce satisfiability 3-sat to graph coloring, to chromatic number, which is graph coloring. And so these edges in this tree are reductions. And if you want to reduce satisfiability to any one of these, you have to go through all these reductions and compose them, but that's okay. When you compose 2 reductions, you get a bigger reduction. You just get another reduction. And the complexity of it is composing the complexity of the 2 polynomials of the 2 reductions, which begets you another polynomial. Remember, we said the nice thing about polynomials, you compose them, you get more polynomials. Multiply them, you still get more polynomials. So these paths in this tree from the root to any node is a sequence of reductions composed together, giving you the reduction from the root to the target node. How many get this schema here? Any questions about that? It's abstract. It's not a data structure. It's a set of reductions arranged in a way that tells you which problem reduces to any other problem via the composition of the reductions along the path between them. So that's what this map, this road map is. Question? No. There's other reductions that could go the other way, but the reduction is directed. If I reduce a problem to another problem, that's the direction of that reduction. That doesn't mean that the problem can't be reduced backwards using another transformation altogether, but that same transformation doesn't quite work in the opposite direction as is where it stands. It needs to be either modified or you have to come up with another one altogether. You know, so remember we gave the example, you're all now engaged in a big reduction of reducing, of having a good life to reducing it to getting a good education. How many remember that example? So you're going to school, why? Because you know more, and why? What's the benefit of that? Well, many, including you earn more money because you know more, you're more skillful, and so on. More companies need you, and so they'll hire you, and so you reduce the problem of having a good life to the problem of earning a degree. And the process, the reduction is you enroll in school and take the classes and pass the tests. Now, if you want to flip it around and you want to say, could you reduce the problem of having an education, of getting an education, to the problem of having a good life? Well, that's a different matter altogether. I mean, there may be a reduction, but that reduction is not simply just enrolling in school and taking classes. Does that make sense? So the reductions are directed. Now, there may be other reductions that are going the other way, but you have to find them, identify them, make sure it works, and prove that they do their job. Just like the first direction. But it's not automatic. Now, having said all that, in this case, there is a canonical, generic way of reducing everything to everything else too, going backwards. Why? Because all these problems have NP algorithms. They have algorithms that are non-deterministic polynomial algorithms. If nothing else, you can have a non-deterministic algorithm for satisfiability that guesses all the answers, one variable at a time, branching 2 ways for true, false on the x, true, false on the y, true, false on the z, and all the other variables. After a linear amount of these guesses, the non-deterministic computation tree will be very wide and it will encompass all possible combinations of guesses. Then you check. Anyway, the height of the tree is the runtime of this algorithm, which is linear. But it's a non-deterministic algorithm, so it's a non-deterministic linear time algorithm for satisfiability. How many get that? Okay. So satisfiability is an NP. And everything in NP reduces to satisfiability. That's Cook's theorem. Now all these things are in NP also. You can guess solutions for each and every one of those. You can guess which is the next branch of the traveling salesman theorem, which is the next branch, which is the next branch, and so on, or the Hamiltonian cycle. Say the next node in the cycle is this, no, it's that, no, it's this. Non-deterministically, guess them all. And after n guesses, you will have a tour, Hamiltonian cycle supposedly, and then you can check to see if it's actually a cycle, if it touched every node exactly once and there's no node left untouched. And then you know, so every one of these problems here has a non-deterministic guessing-based polynomial time algorithm, non-deterministic algorithm. So Cook's theorem reduced all of NP to satisfiability, including all of these problems that are listed here on this slide. How many get that? These are all in NP. Okay. So there's your reduction the other way. If you want to reduce, say, this one back to something that's above it, take that one, see that it's actually over here in NP, all of which reduces satisfiability, and then keep following the arc to whichever one you want to reduce it to. Take the composition of all of that, and there's your reduction backwards, since you asked. Does that make sense? So the short answer that I gave you earlier, it's true. You have to find some reduction goes the other way. It's not the same one. But we just found one that's generic, works for all of them. This was a bit abstract. It's all correct. Any questions about that? So everything that's NP complete reduces to everything else that's NP complete, no exceptions. In fact, everything in NP reduces to everything that's NP complete, no exceptions to that too. All right, so then he just actually gives all these proofs, all these edges in this roadmap, he actually gives them as theorems. And some of them are shorter and some of them are longer, but they're all correct and they're all there, all 21 of them, however many he listed. And then some problems are actually p-space complete, which is even worse than NP complete. And some problems, their membership in NP is not even known. You know, the equivalence of regular expressions. So we don't know if p-space is equal to NP. It's another open question. It's actually harder than the P is equal to NP question, whether P space is equal to NP or to P. They could be all the same. We don't know. These are all open questions. Graph isomorphism, that's still open to this day. There's been recent progress in that. Somebody showing slightly sub-exponential algorithm, but not quite polynomial algorithm. Primes, at the time, it wasn't known whether it's in P. Now we know it's in P. In 2004, some professor and a couple of his undergraduate students proved that primality testing is in polynomial time. You can actually deterministically tell whether a number is prime or not in polynomial time in every case. All right, so problem transformations. To efficiently solve a problem, you transform it to another problem. So for example, satisfiability can become graph colorability, and then if you solve graph colorability, you're solving satisfiability as it is. Let's talk about something interesting, decision versus optimization, a very ubiquitous, powerful concept. So there's two types of generic problems. One of them is a decision problem. I say, here's a graph, and I ask you, is there a coloring? Or is there a Hamiltonian cycle touching every node exactly once? I'm not asking you to find me the coloring. I'm not asking you to find me the cycle. I'm just asking you, yes or no, is there one? Now, if I ask you to find one, that's at least as hard as telling me if one exists. How many believe that? Because if you know what the actual cycle is, I'm sure it exists. And you can easily check if you have a cycle in your hand. You can check if it's a cycle or not, if it's right. If you have a satisfying assignment, supposedly satisfying assignment on your hand, you can plug it in and check to see if it works. So asking you to give me one is at least as hard as asking you to tell me whether one exists or not. Now, it's not necessarily the other way around. If I say, could you tell me if this one has a cycle, and you look at it and do some analysis and say, yes, it has a cycle, doesn't mean you actually have the cycle. You just know that it's there, right? Just like if I say, is there a prime number bigger than a Google? You know there is, because there's an infinite number of them. But if I ask you, then quick, give me one, you'll be hard-pressed to actually name one quickly without going through a lot of computation potentially. Same principle. So the decision problem is just yes, no. Is there an answer? Is there a satisfying assignment? Is there a coloring? Is there a Hamiltonian cycle? Is there a clique, and so on? Okay, so it's a yes, no. But here's the more complicated, potentially, more complicated version is find one. Find me the answer, not just tell me that one exists. So give me the satisfying assignment, right? Give me the three coloring, give me the Hamiltonian cycle, or give me the clique that you claim is actually there. Now, surprisingly, we're about to show that they're equivalent. If you can consistently solve using a subroutine or an algorithm the decision version in polynomial time, you can also solve the actual optimization version that gives you the answer in polynomial time also. The opposite is obvious. If you can tell me what the answer is in polynomial time, you can certainly tell me that it's there in polynomial time. Just convert the answer to a yes. And if there's no answer, then convert that to a no. And it will take the same time what it took before, plus one more time step saying yes or no. But the opposite is not so obvious. If all you know that there's an answer, how do you actually extract the answer? Using polynomial time as well. So we're about to prove that. So the theorem again is solving optimization problem is not any harder, polynomially speaking, than solving the decision problem. It's not so obvious. Not obvious at all, actually. So once we do that, suffice it to talk about problems that are only decision problems, just yes-no problems, Boolean formulas, Boolean questions. The answer is always yes or no. Not the answer is what is the assignment, or what is the coloring, or what is the Hamiltonian cycle. Just tell me whether the one exists or not, yes or no, and that's enough. Because we're about to show that the two are the same, computationally speaking, with respect to polynomial time. All right, how do we do it? The idea is to build an optimizer from a decider. So let's say you have a decider for satisfiability. It just says, yes, this formula is satisfiable. You give a formula, it says yes, or it says no. It doesn't give you the answer, what the satisfying assignment is. It just tells you whether it's satisfiable or not. But you're after the actual assignment. So how do you figure out the assignment if you have a subroutine that just says yes, no for every formula that you give it? Well, let's see what happens if you just give it a formula that's slightly different. So let's say you ask the decider, you have some formula P. Let's say it's this one. It doesn't have to be that one. It could be much longer, more complicated formula. But let's say it looks like this. And then you ask the decider a couple of questions, and really one question in particular. You ask it the question, is P and X as a separate formula? Because P is the formula for which we want to know the actual satisfying assignment, if there is one. So ask it whether P and X as a slightly larger formula, because it has an and X appended after the P, ask it if that's satisfiable. And it's a black box. It always looks at the formula, always tells you the right answer, whether it's satisfiable or not. Always in polynomial time, presumably. So if it says yes, it's satisfiable, a couple of things can happen. If P and X is satisfiable, you can infer what about the value of X in a satisfying assignment for P. So let's say it says P is satisfiable. Then it says P and X is satisfiable also. What can you tell me about X, the value of X in some satisfying assignment for P? It's not a trick question. It's very straightforward. That's a hint. What must X be in some satisfying assignment for P? Not necessarily all of them, but in some of them. But X is satisfiable, right? If you assign X to 1, it's satisfiable. Right? But X is equal to 1 in some satisfying assignment for P. Because if you set X equal to 0 here, this whole thing will be false. But P by itself is satisfiable. So if P and X is to be satisfiable, X must be 1 in some satisfying assignment for P. How many get that? Because if X couldn't be 1 in any satisfying assignment for P, P and X couldn't be 1. couldn't be true. And then P and X couldn't be satisfiable. So if it says that P and X is satisfiable, if it says a yes, you know for sure that X must be true in some satisfying assignment for P. Could be other satisfying assignments for P. Actually, could there be a satisfying assignment for P where X is false? There still could. But then P and X, if they were all like that, where X was false, then P and X wouldn't be true. So if P and X is true, and it says yes, there is some satisfying assignment where X must be true. Otherwise, the AND will cancel all that and make it false, and then P and X would be satisfiable, and then it won't say yes, it would say no here. Because the decider is always correct, whatever it does. Yep. It's the same variable. So this X here is that X there. I just painted it purple, not red, but it's really that red X here. I wanted to make it the same color as the actual formula P. But yeah, it's exactly the same X. Good question. All right. And if it says no, then what do you know? Then X must be false. If P and X is not satisfied, then X must be false. So the opposite question, P and X not, is sort of the inversion of these two conditions. So I'll just spell those out. P is not satisfiable if it says no. And there's a case where it's actually interesting. If it says if P and X is satisfiable and P and not X is also satisfiable, that means the value of X could either be true or false in some satisfying assignment for P, which means X is kind of a don't care, like the don't care from Boolean logic, design. It's X could be either false or true. It doesn't matter. P is still satisfiable either way. So that's sort of all the possibilities here. But really, all you need to do is ask it one question. I'm just showing you what happened if you ask it the opposite question as well. So if it's this case is also kind of unique because if you say P and X is, it says it's not satisfiable. If it says P and X not is not satisfiable either, then either for the value of X being true, it's not satisfiable, or if you fix the value of X to be false, it's not satisfiable either. That means it's not satisfiable in any case, in either case, and it's just not satisfiable in general. So by asking this oracle or this subroutine that is a decider, it says yes or no, it's satisfiable or not, you ask it a simple question, if P and X is satisfiable, based on what it tells you, true or false, you know what the value of X is in some satisfying assignment. You don't know the value of Y or Z or W or any other variable, but you know the value of X in some satisfying assignment, not necessarily all satisfying assignments. At least one of them, X must be true. How many get that? Okay. So you basically forced the decider to reveal the value of X to you by asking it this question about P and X. All right, so now you know one bit about your answer, the value of X in some satisfying assignment for the formula P. What are you going to do next? What are you going to do about Y and Z and W and the other variables? Because you need those values too. You have a decider, but you want to exploit the decider into being an optimizer giving you the actual answer. Yeah. So now you say, okay, if P and X is true, then ask it, what about P and X and Y? And then get the answer, and then say, what about P and X and Y and Z, and so on. And by the way, if it says no, it's not satisfiable, you need to ask about P and X not and Y. How many understand that nuance? So you have to either ask about the variable or its negation based on the yes/no answer that you got for that variable. That's what you're going to do the next round. In other words, you're going to repeatedly query this decider many times. Each time it will give you one more bit about the answer. And eventually, after a bunch of iterations, how many iterations? After a bunch of iterations, you will know all the values of all the variables in some satisfying assignment for P, which means you have the answer. How many iterations? Roughly. How many? Let me give you an analogy, and then we'll ask the question again. How many have actually went through a process like this in your own personal lives? Can you give me examples from a personal life? Yeah, how many played 20 questions or 21 questions, whatever? Okay, so you did exactly this. So I have some object in my head. I'm trying. You need to guess what it is, but I can answer yes/no questions. So first you say, is it an animal or a mineral? Does it have? Okay, if it's an animal, all right. Does it have 4 legs versus 2 legs? Does it crawl? Does it fly? Does it walk? Does it swim? Right? You ask me Boolean questions, and I say, yes/no to each one of those. And after about 18, 19, 20, 21 questions, you know for sure it's a zebra. How many have seen this game, experienced this game? Okay, that's exactly what's going on here. We're playing 20 questions or 21 questions with this decider, one question at a time, forcing it to narrow and narrow and narrow the space of answers until we know what the answer is altogether, one bit at a time. And in the game of 20 questions that the kids play, grade school, each bit is one of those questions. Fly versus walk, swim versus crawl, legs versus, fins, or whatever the questions are. And that cuts down the space by half, roughly, every time you ask a question. So roughly, how many objects can you differentiate? This is the part where kids will probably not know the answer to, but how many objects do 20 questions allow you to differentiate among, ideally, roughly? Yeah, about 1 million different objects, 2 to the 20. So let me ask you that question again from 2 minutes ago. How many iterations do we have to go through here? Yeah, it's about n iterations, 1 per variable. So it's not exponential, because the kids will be spending a long time in grade school if they had to go through 2 to the n Q&As about the zebra. Okay? Any questions so far? So you've all done this. And this is a general technique. This is how you can turn any decider into an optimizer. You're building an optimizer from a decider. What's an optimizer? Something that gives you the answer. What the decider tells you if the answer exists or not. That's a lot weaker. Yeah, I know there's an answer. That doesn't tell you what the answer is. Yes, it does. With 20 questions, you'll know. And by 20, I mean a linear number here. Linear in the number of bits in the answer. So if the answer is n variables or n nodes in the graph or n colors or whatever the parameter is, that's how many iterations roughly you have to go through. That's it. But it's a polynomial number. In fact, it's linear. It's not just any old polynomial even. Even if it was quadratic or cubic, it'd still be okay. But it's not even that. It's a linear number of questions. So once you have a yes/no subroutine or black box or decider, you can always exploit it, play 21 questions with it, and squeeze the answer out of it 1 bit at a time. It has no choice but to yield the answer to you 1 bit at a time, 1 bit per question. Any questions about this? Very general, very powerful technique. So without also generality, from now on, all we need to talk about is yes/no questions. Because if you settle how fast you can answer something yes, no, whether there's a solution or no solution, just apply this and then you'll actually get the solution, so you don't even have to do this. Just solve the problem of how fast you can say yes or no to whether a solution exists or not, and you're done. Because then you can always apply, as an afterthought, the game of 21 questions to that subroutine that you just came up with, so that algorithm. So suffice it to just deal with, analyze, and think about yes/no questions. How many get that part? That's the leap that we just made. And that's a lot easier to deal with yes/no Boolean formulas or Boolean queries than to deal with arbitrary queries that give you arbitrary things. There's a lot going on there. The point is you don't have to deal with questions or problems that give you arbitrary solutions, just yes/no answers, whether there's a solution or not. That suffices. Because once you have that, run it in a tight loop, play 21 questions with it, and you'll actually get the answer that you seek from something that just tells you whether there's an answer there or not. It has no choice but to yield. that information through 21 questions. Okay, any issues with that? Okay, it's a very general, very powerful technique. So a few more transformations, graph cliques. You have a Boolean formula, you want to reduce it to graph cliques. So basically you create a graph so we're proving a graph clique is NP-complete, right, on this slide. So take this Boolean formula, create these nodes from it. So red variables become red nodes, green variables become green nodes. So this is a formula, that's a graph. That's not a formula, this graph. This formula is not a graph. But from this formula, we create a graph such that this graph will be three colorable. This graph will have a three clique if and only if this Boolean formula is satisfiable. So basically, you connect every node to every node that's compatible with it according to this formula. So X is compatible with Y naught. It's not compatible with X naught. It's a logical contradiction, and so on. So once you just connect every node to every node that it's compatible with, and you do it in all possible combinations, a K clique in this graph will correspond to a 3-sat solution in this formula. So for example, this clique here from X to Y naught to Z naught will correspond to the solution X is true, Y is false, Z is false, because these are knots. And there's many other cliques here too of size 3. There's many triangles in this graph, and those will correspond to other solutions too. So the solution is not unique, obviously. So if you can solve K clique, you can solve satisfiability by transforming it into a graph and then looking for K cliques in this graph. K being the number of variables in the formula to begin with. So that's a transformation, that's a reduction, that's the F from A to B. A was satisfiability, B was graph cliques. So we reduced the problem of satisfiability to the problem of graph cliques. And because all of NP reduces to satisfiability, that's Cook's theorem, here we see the satisfiability reduces to graph cliques, composes two reductions or transformations, and all of NP then reduces to K clique, which makes K clique NP complete, because K clique itself is an NP as well, guess and verify non-deterministically. So that's a proof that the clique problem in graphs is NP complete. Any questions about that? So you see, now we can prove problems to be NP complete in quick succession without resorting to first principles, brute force approaches like Cook did in his own original theorem. We're building on the back of that. Right? So, of course, once you can determine the decision version of clique, you can also determine the actual optimization version of clique, same as we did on the last slide, 21 questions. So we'll kind of leave that assumed as we go. So I won't have to repeat that every time. It's just an obvious thing to do. Once you have a decision version, a decider, you can always turn it into an optimizer by playing 21 questions with it. So clique is NP complete. Independent set. Independent set is NP complete. What is an independent set, by the way? Independent set is the opposite of a clique, right? So it's an anti-clique. So independent set is a bunch of nodes, none of which are connected to one another. Just like a clique is a bunch of nodes, all of which are connected to one another. So here's a graph, and I want to say, is there a clique of size 4? And yes, there is. This, and this. These 4, all of them connect to one another with a K4, K sub 4 here. Okay. And sure enough, the same nodes in the complement of the graph are independent set. So if you take a clique and you negate this graph, so this blue graph is a negated version of the green graph. Edges become non-edges, and non-edges become edges. We just flip all the edges and non-edges to get from the green to the blue. So whatever subset was a clique here will be an anti-clique there, or an independent set. Right? So this is a pretty straightforward transformation, even simpler than the last one. So if you had a subroutine that can compute independent sets, automatically that will translate into a subroutine that can compute cliques simply by inverting the graph. Turn edges to non-edges and turn non-edges to edges. How many get this? Okay, this one's pretty straightforward. And its transformation is this reduction F. A is this problem of clique, B is this problem of independent set, and it works in polynomial time, obviously, because how hard it is to negate all the edges. It's pretty straightforward. It's linear time. Right? It's not even quadratic or cubic, and if it was, it'd still be okay. So basically, we built a clique solver from an independent set solver, simply by flipping the graph over, flipping, negating edges to non-edges and non-edges to edges. Well, which makes independent set NP-complete as well. Because we already proved that everything reduces to clique. What was the proof for that? Well, we had that on this slide. So you see, once we show a few problems NP-complete, we can show lots and lots more problems NP-complete by reducing from them and composing all the reductions, all the way from Cook's theorem, all the way through the sequence of reductions to the problem at hand. And all these reductions compose, and they're all polynomial times, so the composition of all these polynomials is still a polynomial, and just you have one more big polynomial composed reduction end to end. How many get this strategy? I only see now 3 or 4, 5, 6, maybe 10 hands going up. Ask me questions about this. What are we doing here? Philosophers have been asking themselves that for centuries. What are we all doing here? What are we doing here is proving that problems are NP-complete. That all of NP, this large and complex set of problems that we've been trying to solve for decades by the thousands of different variations, are all in this class, and they all reduce to each one of those specific problems. Independent set, and before that satisfiability, and in the middle it was 3-sat, and clique, and so on. So Cook did the first one for us, and that was hard because there was nothing to fall back onto. It was the original one. It had to be done brute force from scratch, using Turing machine states and transitions, and so I had to encode all of that as one big Boolean formula that was satisfiable if and only if the Turing machine accepted its input, and it was an arbitrary polynomial time Turing machines running on an arbitrary input. In other words, it was an arbitrary language in NP, or problem in NP, however you want to think about it. So you had to do the brute force hard way from scratch. Once he did that, we have an easier time. He reduced all of NP to sat. Now all we got to do is prove sat to 3-sat. And using his transformation, our little, much simpler transformation composed, is all of NP to our little 3-sat. How many get that part? Okay, so that was good. But once we have sat and 3-sat, now we can do other things beyond that. So here's 3-sat reduced to graph cliques. Okay. Graph clique in this graph will be a solution to 3-sat here because it's a bunch of compatible values represented there. And once you have clique, you can reduce it to independent sets simply by flipping the graph edgewise. And on and on and on it goes, and thousands of problems have been shown to be NP-complete since, probably tens of thousands of ubiquitous common problems. The actual class is infinite, right? And that's how these reductions go. So it's about transformations, right? And some of them can be very tricky. I just showed you a few relatively simple transformations. Cook's one was not that simple. I mean, it was formidable because it was the first and there was nothing to fall back onto or copy from, and it had to be done generically from Turing machines. But here's one from graph colorability. So this one is not so obvious. It's kind of mid-range between the simple ones that we saw so far and Cook's theorem. So you take a Boolean formula one clause at a time, and each clause becomes, so we're talking about 3-sat, by the way. So now it suffices to reduce from 3-sat, because we know 3-sat is NP-complete. All of NP reduces to 3-sat through sat and Cook's theorem. So take every clause that has 3 variables, because it's a clause from 3-sat, so we know it's 3 variables. It's not more, it's 3-sat. Construct this piece of a graph from it that basically acts like a big OR gate. So we call this kind of a gadget. This gadget, it turns out, is colorable if and only if the values of these nodes are true, and these are really colors, not values, but we assign one of the colors to the value true, another color to the value false, and the third color would be none of the first two. The third color is the non-true, non-false color. It's just some other color. So once you do that, every clause becomes sort of this graph piece that behaves like an OR gate, which is 3 colorable if and only if this Boolean formula clause is true, which means one of these 3 inputs has to be the true color. One of these has to be blue, in other words. And then we attach all these other triangles, true to false, to this third color separately from every variable to its negated variable to this third color. By the way, this green is the same as that green. It's the same node. I'm just displaying it twice, but it coincides. These two nodes are the same node. I'm just showing it to you twice here. So you can see the triangles. So bottom line is, once you apply this construction, you take a Boolean formula in 3-sat form, 3 variables per clause, and then you apply this gate for each clause, and then you have these 2 triangles. One of them is a family of triangles, every variable to its negated version. But you take this, and for this first clause, here's a copy of this piece of graph. I just distorted it a little bit so it fits better on the screen. And then this is the x and y and z clause here in red, so that's why I color-coded this red. And then you have another copy of this piece of graph, this other OR gate. Of course, now the z is already there, so I don't have to have another z. I just connect it to the z that's already there, and there's that z there. So the z is here in red, and that z is here in green too. And it's the same z, so I don't need to display it twice. And that's that clause represented there as a piece of graph. And then, of course, the last clause, the blue one, so there's the blue one. Again, the x naught and the y are already there. I need the z naught because that's a new one, so I put that in. Right? That's the third clause. And then I implement these triangles. So here's the blue, here's the red, here's the green, and here's this purple triangle. So this purple triangle here is this long purple triangle there. It's still a triangle, it's a graph, so it doesn't matter how long and distorted it is, it's still a triangle among 3 graph nodes. Right? Graph is topological, it doesn't matter how you display it on the screen as long as the topology is respected and preserved. Right? You can move these nodes around, it'll still be the same graph, right? As long as you preserve the edges, the connectivity. So, and then you have these triangles here between every variable, its negation, and the green node. So I'm adding this family of triangles here in blue for every variable. So y will be connected to y naught, which will be connected to the green. Z will be connected to the z naught, which will be connected to the green. So finally, I end up with a big graph. And this big graph will be 3-colorable if and only if the original formula is satisfiable. And not only that, if you find a 3 coloring for it, and I just computed for you a 3 coloring for it, you can actually check that no 2 adjacent nodes have the same color. You can just read off the answer to the satisfying assignment from this valid 3 coloring for this graph. So y will be false, x will be true, y will be false, and z will be false, for example. And there's other ways to 3-color this graph, which correspond to other satisfying assignment to this formula. It's not unique. All we need is 1. Right? So we just read off the values. X is true because it's blue, y is false, z is false because they're red. And if you check in this formula, if x is true and y is false and z is false, this whole formula becomes true. It's satisfied. So what have we done here? We took an arbitrary Boolean formula, converted it to a graph in such a way, in a constrained, clever way, that this graph is 3-colorable if and only if the formula is satisfiable. So if you can have some subroutine or some oracle or some person or some piece of code that can quickly tell you whether a graph is 3-colorable, you can exploit it in this way to tell you whether a formula is satisfiable, which means graph coloring is NP-complete. We transformed all of NP into graph coloring. Through Cook's theorem first into satisfiability, from satisfiability into 3 satisfiability, from 3 satisfiability into this graph colorability, compose all 3, and you have a reduction from all of NP to graph coloring. That's a polynomial time reduction. How many sort of get this? I don't expect complete understanding here, but okay, that's good. That's, about half the class sort of get it, which is, I'll take that as a win. Because this is a clever transformation. That little pieces of graph can act as OR gates, and you connect them, because this is about colorability. It's not about Boolean anything. Formula is about Boolean values to variables. This has no variables. It has nodes. It has no Boolean values. It has colors. So how is coloring a graph equivalent to assigning Boolean values into a formula? Well, this is how. I just showed you that they're equivalent. The transformation does it. Just like you might ask, how is taking classes and passing exams get you to a better life? It feels kind of miserable sometimes, right? Cramming and the stress of exams and getting a bad grade, and how is that a better life? Well, we already talked about how it's a better life. Because by the time you're done with all this, you'll be a lot more skillful. A lot of companies want to hire you at a higher rate and give you a lot of money, and with that money you can buy a lot of things that will get you a better life. That's how. That's the transformation. And just like in real life, it's not obvious to some people, this transformation. Those people aren't here. They don't go to school and they don't have such good lives. They kind of live mouth to hand and paycheck to paycheck, and they end up in debt, and they argue with their spouses. Lack of resources ends up creating a lot of strife in your life, potentially, unless you're a Buddhist monk. But the point is, some transformations are not so obvious. I mean, even going to school, it's not obvious that, that's the key to a better. Most people get it, but some people don't. Still, after all these centuries of trial and error and evidence and so on. Okay. So this transformation is a tricky one, is a clever one, is a non-obvious one. The one about independent sets and cliques, flipping edges, that's pretty straightforward. And some transformations, just so you know, are so much more complicated than this. NP-complete transformations, showing that from problems NP-complete. They'll take 100 pages of a PhD dissertation just to describe the transformation and prove that it actually does what it's supposed to. And people have done this. Create hundreds of pages of complicated kind of transformations. So some of them are horrendously complicated, way too complicated to even explain, in a textbook, much less in a lecture. It would take dozens of hours to describe the whole thing. Obviously, we're not going to do any one of those. But I just want to tell you, they're out there. They can get arbitrarily difficult. Just like pieces of code can get arbitrarily complex. All right, so you might ask, what makes colorability difficult? Is it the high degree of some nodes? What if we restrict all the degrees to a very, very small degree? So if I say the max degree of any node is 0, and I say, is it 3 colorable if the max degree of any node is 0? What do you say? Is it 3 colorable? I'm going to say, yeah, it's 3 colorable if the degree is max 0. Okay, why? Yeah, nothing's connected to anything else. In fact, it's 1 colorable, not just 3 colorable. 1 color suffices. Nothing is connected to anything else. Make everything blue and you're done. So 0 degree 3 colorability is trivial. The answer is always yes. What about 1 degree max? If the degree of any node is at most 1, and I say, is it 3 colorable? What's your algorithm now? Yeah, you only need 2 colors, and it's not even a line exactly, because a line will have degree 2 somewhere, not degree 1. So if the degree is 1, it's even simpler than a line. What is it actually? I mean, she's almost right. Yeah. It's a bunch of pairs. So it's a bunch of little lines, not even a big line. All right, so that one's pretty straightforward. What if the degree was at most 2? Now we're getting into long lines. Or not just lines. Could be something else. Could be cycles. A cycle where the 2 ends coincide, that's a line that connects to itself end to end. That could be there too. So do 2 colors suffice for max degree 2? If it's a long line, yeah. Blue, red, blue, red, blue, red, blue, red. But if they're connected end to end, something else can happen. Yeah, if it's even, we're good. If it's odd, blue, red, blue, and if the ends are connected, even if it's a triangle cycle, you need 1 color, another color, and a 3rd color yet. 2 colors don't suffice anymore. Now it gets a bit tricky. If I say it's 2 colorable, you have to look for odd cycles. If I say it's 3 colorable, the answer is yes, if the max degree is 2. So the algorithm gets a little bit more sophisticated, if you can call that sophistication. It's just an if statement. It turns out for max degree 4, it's NP-complete already. So, and I'll leave open the case for max degree 3 for you to dig into for extra credit if you'd like. But So we won't spend too much time on this. For max degree 4, to show it's NP-complete, we come up with this gadget that has max degree 4. It's 3 colorable, but not 2 colorable. And any 3 coloring, the corners get the same color. And once you do that, we're not going to harp on all the details. I don't know it's worth the time. But once you do that, you take this gadget and you replicate it a few times. Once you do that, you have a slightly larger gadget, but all of its properties are inherited from the smaller version of the gadget. It has max degree 4. It's 3 colorable, but not 2 colorable. And you can check all that. All the corners get the same color in any valid 3 coloring. And then you do substitution. High degree nodes get substituted with that. And if you have an example of a graph that has high degrees, you substitute that gadget in there in such a way that once you reconnect, this new transformed graph is 3 colorable, if and only if the original graph was 3 colorable, but this graph has a max degree 4. And I skipped over a few details. Actually, all the details were in the slide. I just kind of rushed through it because I want to talk about more important things very soon. So once you do that, you realize the max degree 4 graphs are just as hard to color as any arbitrary graph. So it's not about the degree, 3 colorability, and it's not about the planarity, whether a graph could be embedded in a plane without any 2 edges crossing, which makes it a planar graph. Planar graphs are just as hard to color as arbitrary graphs, it turns out. And again, the proof is this. You create a gadget. It's a local substitution scheme. The gadget is planar, obviously. No edges crossing. It's a planar embedding. It's 3 colorable. Here's the 3 coloring of it. And in any 3 coloring, opposite corners have the same color. So you can enforce that condition. Bottom line is, once you have this gadget, you can take edges crossing of a non-planar graph. Actually, this is still a planar graph, but it's a non-planar embedding of a planar graph. But that's okay. Take any edge crossings that you want to eliminate, replace it locally with this gadget, reconnect, and what you have is a new graph that's 3 colorable, if and only if the original graph was 3 colorable, except this graph is planar. There's no edges crossing there. So this notion of a graph being non-planar, and most graphs are non-planar. Planar graphs only have a linear number of edges and nodes. Non-planars could have quadratic number of edges, so most of them are non-planar. So planar graphs are just as NP-complete to color as arbitrary graphs, is the bottom line. So we just went through 2 more NP-complete proofs. I rushed through them, but all the details are on the slide. And of course, you can compose graphs to be degree max 4 and planar together, and all you got to do is compose the last 2 reductions. So there's something about colorability that it makes it very tricky. And it's not about the size, it's not about the number of colors, because even 4 colorability or 3 colorability is already NP-complete. And it's not about the graph being planar or not planar that makes it hard, because even for planar graphs, which are a simpler, smaller subset of the graphs, that's still NP-complete. And it's not about the degree either. Even if the degree is restricted to be 4, that's still NP-complete on top of that. So there's something about colorability that's just very, very difficult to achieve. So now we're exploring sort of the other parameters, knocking them down to very small values, and showing you how the problem still remains NP-complete. It's so hard. Okay. Just like we did that in decidability. We showed that the halting problem is undecidable even if the input is fixed at an empty string. It's still undecidable. Right? And in fact, almost every variation of it that's not trivial is undecidable too. All right, so that's about graph colorability. If the graph is planar, actually, it turns out that 4 colors always suffice. It's actually a mathematical theorem to that effect. And colorability actually can be investigated on lots and lots of different surfaces or manifolds, like toruses and double toruses, and the minimum number of colors necessary to paint a map that's planar to the surface, whatever that surface is, not just a plane, but on a sphere, on a torus, on a double torus, and so on, is related to the number of holes or genus of the surface, and it's roughly related to the square root. But anyway, that's probably more than you want to know about colorability. But it's a very, very applicable practical problem. When you assign jobs, you schedule jobs, either a job shop or processes on a CPU that use registers and things like that, you can create a colorized version of a graph that has the conflicts among the jobs, right? So 2 tasks have an edge between them if they're conflicted in some way, they're dependent on one another, like if they use the same resource, two threads use the same register, well, there'll be an edge between them. Or two people use the same tool like a hammer, then there'll be an edge between them and so on. So you can only schedule non-neighbors in any given time period so they can not have contention on the register or the hammer, whatever the tool or the resource that they need to use concurrently. And once you do that, you can use different colors for every level of this tree, and this becomes your schedule. And the question is, what's the minimum number of colors needed? And that's the total minimum number of time periods needed to execute all these tasks in parallel and not have collisions on the resources that they must share, like a register on a CPU or a hammer in a shop that, if there's only one hammer. No two workers can use a hammer at the same time, obviously. So I'm just showing you a reduction of scheduling without conflicts to graph coloring as one example of what you use graph coloring for. In fact, compilers use this reduction and use heuristics for graph coloring to schedule threads and jobs on a CPU in real time, millisecond by millisecond, so that they avoid collisions on registers and caches or whatever the resources are that must be shared among these threads or processes exclusively. Right? Mutual exclusion. So this is what I just said. Okay. So again, the map of where we've been. We explored for the last couple of lectures P and NP right here. They may or may not be the same class, we don't know. We gave a lot of examples of problems in NP, like SAT. Now you know what this problem is, SAT. Now you know what NP-complete means. And the importance of SAT is a ubiquitous problem that's NP-complete. Whether it's in P or not, we don't know, but for sure it's in NP. It's NP-complete, which means all of NP reduces to it, which makes it the hardest problem in NP in some sense. But of course, that title is not unique to SAT. All these other problems that we saw are also NP-complete, including partitioning and knapsack and traveling salesman and Hamiltonian cycle and Steiner problem and on and on and on. All these long lists of 21 problems that Karp had in his paper and thousands of others that we know of since. So we explored this region of the map. Of course, earlier in the course we explored context-free, deterministic, regular, finite languages over here. At some points we alluded to problems that were exponential time and polynomial space. We definitely explored decidability and decidable problems in this big oval, and of course problems that are recognizable like the halting problem but not decidable. And we also explored some problems which were not even recognizable, like the converse or the complement of the halting problem, H bar over here. So we've sort of been through many places on this map with detailed explorations and theorems, and the latest is P and NP in red here. Any questions so far? So where we've been and where we are and where we're going. So given that NP is so ubiquitous of a class of problems, and almost every interesting problem we're trying to solve in everyday life is NP-complete. Traveling salesman and scheduling and so on and so on. We still need to solve these problems fast, right? A driver gets into a truck for FedEx and has 50 packages on board, and they have to deliver all 50 packages. So what route do they choose? I mean, which house do they go to first, second, third, fourth? That makes a huge difference, right? They're trying to solve traveling salesmen right there and then, every morning when they get into their trucks. How many get that? And it's NP-complete. So what, are they going to take a random route? That can be very, very bad. They can just jump back and forth right across the city house to the next house to the next house and the next house to the next house, crisscrossing the whole city 50 times. That's terrible. It'll never happen in one day even. Never mind waste a lot of fuel and precious billable hours and so on, and customers will complain about getting it quickly enough. So they have to solve some version of traveling salesman well enough to do that job that one day, but not necessarily solve it exactly with the best possible solution, optimizing every last mile and foot and inch out of that trip. They just need to solve it close enough. So we're about to show how to come up with heuristics that solve these problems close enough in practice. By close enough, I mean no worse than a factor of 2 from optimal, or 1.5, when we don't even know what the optimal is, because it's impossible to do in polynomial time, potentially. We don't know how to do in polynomial time. But in polynomial time, we can certainly, or even linear time, we can certainly come up with a solution that's no worse than twice the optimal. And that's a good guarantee to have, which means the packages will get there at most twice as late as they can possibly get there in an ideal universe where we can get them as quickly as you can using some omniscient algorithm that doesn't care about time or space, but no worse than twice. It'll not be 50 times or 1,000 times or 1,000,000 times as bad, which could happen if you're just not careful. All right, so when it comes to solving algorithms, we look for speed of the algorithm and the quality of the solution. Is it exact, or is it twice as bad, or arbitrary amount of bad? Ideally, you want it fast and exact. You want it short and sweet. Get the answer fast. But sometimes you can't both have it fast and exact. You get it slowly but surely, brute force. So exact, you can try all possibilities. It may be slow, but it'll get you the right answer, the exact, the optimal, the best answer, but it'll be very, very slow. But in practice, that's no good. You can't compute all possible k factorial different permutations for that truck's route that day for FedEx for that truck, because k is 50 packages and 50 factorial is too large of a number. So you want to approximate quick and dirty solution. You want it fast, approximate is good enough as long as it's not too bad. And of course, in some problems they're so hard that you can't even approximate them quickly. Even approximations will be slow. Those are really bad. You'll get your answer too little too late, and that's not what we want at all. So we want to be in this quadrant ideally if we can't be in that one. Okay, so that's what we're going for next. So like for example, when you sort, you're in this quadrant. Short and sweet, n log n, quick sort, bird sort. But for a traveling salesman, you're in this quadrant. You come up with some heuristic, good enough, say no worse than twice optimal, and you get it quickly, and you don't have to spend forever computing it. All right, the problem is the solution space has very long, deep crevasses that you can have a hard time finding. So if you look for pure greed, you may get stuck in local minima. Now in some scenarios, greed is good. Who said greed is good in some famous movie? Greed is good. Famous speech. Any movie buffs? Anyway, think about it. If you use pure greed, you may get stuck in this local minima, strictly hill down descent. But the real solution might be in some very narrow, deep crevasse that you won't stumble upon very easily. And that's the problem with greed. It gets you into low valleys, sure enough, but this valley here is not the best you can do. There's a much deeper, narrower valley here that if you just take steps, you will just completely skip over because it's a very, very tiny, narrow valley that is easy to miss unless you look at the entire solution space, which is exponential. So that's generally the problem with greed. Gordon Gekko in Wall Street, by the way, said greed is good. So we're looking for examples of problems that we can solve with good approximation heuristics pretty fast and get almost optimal solutions, not necessarily optimal, but good enough. And there's lots of approaches to it over the years, including from branch and bound and integer linear programming and even genetic algorithms, which I kind of put in the class I call wishful thinking, simulated annealing and genetic algorithms. You've probably seen some of those. Even machine learning is in this class of wishful thinking. You hope that the algorithm will somehow magically fall out of a machine if you put enough neurons and interconnections between the neurons and run some machine learning simulation. But even when it works, you can't really explain why it works. And even if it works and you want to modify it slightly, you can't. You have to start from scratch. And there's problems with these kind of algorithms. They work well enough for some scenarios, but don't make the mistake of using them first before trying much simpler, deterministic, well-understood heuristics that may work just as good or even better. So for example, vertex cover. Let's see how we can solve that quickly using a heuristic. Now, we already saw that vertex cover, an independent set, and all these other ones are NP-complete, so it's NP-complete. There's no hope, practical hope of solving it exactly in polynomial time, but here's how you can solve it no worse than twice. Okay, so and this was originally one of Karp's problems in this paper. And vertex cover, here are some vertex covers in green for graphs. It's not obvious at all, especially if the graph gets complicated, that the green is a vertex cover, much less a minimum vertex cover. You have to actually start checking everything. So again, what is a vertex cover? A vertex cover is a minimum set of vertices that touch every edge. right? So this is a vertex cover between these three vertices in red. I'm touching this edge, this edge, this edge, this edge, and that edge by at least one of the red vertices. So not all the vertices have to be chosen, but the ones that are must together between them touch every single edge, at least from one end or the other end. But that's also a vertex cover, the 2 here, because these 2 red vertices touch every single edge in the graph, and 2 is better than 3 because it's less. So it's a better solution. So how do you find the minimum vertex cover? So here are some examples. Here's the heuristic that gets you no worse than twice. Okay, and we can prove actually separately that there's no way to approximate it to arbitrary amount of precision, and unless p is equal to np, and the best known algorithm is exponential time that we know of, and so on. But we can solve it within very quick linear time, no worse than twice the optimal. And it's so easy that I can do it in 2 minutes before class is over. So here's the algorithm. You pick a random edge, any edge you want, like this one. Take the 2 endpoints, the 2 vertices on both ends of that edge, throw them into your solution. All right? Eliminate those 2 vertices from the graph and all of their adjacent edges. So I eliminate these 2 vertices I just put in the solution and all of their edges, and all remaining, for the remaining graph, just repeat this process precisely as you did before. Find the random edge, select it, put in the 2 vertices of the 2 ends of that edge into the solution, add them to the solution, union them into the solution, and keep going until the graph is completely exhausted. And by the time you're done, the set of vertices that you picked will cover all the edges. How many believe at least that part? Not that it's good, that it'll do the job. It'll cover all the, because for every edge you selected, you put in the 2 endpoints which cover that edge and every remaining edge around them, like this one and this one and this one. And once you eliminate those 2 touch all of these that are eliminated, and you keep repeating it for remaining edges. By the time you don't have no edges left, they're all being touched by all the nodes that you selected along the way, unioned together. So it's obviously a node cover. Now, why is it a good node cover? Why is it no worse than twice? Well, because every edge has to be touched by at least one node. So it has to be touched by at least this node or that node. So at least one of the 2 red nodes must be in any node cover solution. Otherwise, that edge will not be touched by anything. And that's not going to be a solution. So at least the x or the y must be in a solution, in a node cover, for this red edge to be touched by at least one of them. And one of them must be there, and I'm taking both of them in. So maybe both must be in a solution, in the optimal best lowest number solution. One of them must be there, but I'm taking both of them in. So and I keep doing this. I keep taking 2 when I must take at least 1. I take 2. And then the next edge when I must take at least 1, I still take 2, and so on. So at the end, I will take no more than twice what I actually minimally had forced to be taken to begin with. How many get that? Good. And that's why this solution is no worse than twice the optimal, guaranteed. And this problem is NP-complete. And this algorithm, look how simple it is. It runs in linear time. It's very, very simple to describe even. And it guarantees you a solution is no worse than twice the optimal, and you'll never know what the optimal is. All right, so next time we'll talk more about heuristics and a few other things.